All right, here we have lesson 6 on exponential functions. Okay, we already looked at linear functions and how they have a constant rate of change. Remember, the rate of change is the slope. It's the change in y over change in x. Now we're going to investigate exponential functions, okay? An exponential function is any function that has a variable where an exponent should be. So check this out. Consider the exponential function f of x equals 3 times 2 to the x, where this x up here is the variable and it's in the exponent spot. So let's evaluate this. What does it mean to find f of 2? It means I'm going to plug a 2 in, evaluate the function f at 2 by plugging a 2 in for the x. So I have 3 times 2 to the second power. In other words, I have 2 to the second power, which is 4, or 3 times 4, which is 12. F of 0, I would do the same thing. I want to evaluate this when x is 0. So I have to remember my rules of exponents. Anything to the 0 power is 1. So remember, this is my base. So that becomes a 1. It tells me I have 3 times 1, which is just 3. And here I have f to the negative 1. So I have 3 times 2 to the negative 1. Well, anytime I have a negative exponent, I take the reciprocal of the base. So the reciprocal of 2 is 1/2. So I have 3 times 1/2, and that tells me I have 3 halves, or 1 1/2. So if I want to calculate the average rate of change over the interval from negative 1 is less than or equal to x is less than or equal to 0. In other words, over this domain, I want to find the average rate of change. So I use these as my x values, and I've used the y values that correspond to them. So when x was negative 1, remember, by the way, rate of change is change in y's over change in x. So what I'm looking for is the change in y over change in x. So from negative 1 minus 0, and when the y value, or I'm sorry, when the x value is negative 1, the y value was 3 halves, or 1 1/2. So I'll put in 3 halves. And when the x value was 0, I had a y value of 3. So 3 halves minus 3. Well, this 3 is the same thing as 6 halves, and that would tell me I have negative 3 halves over negative 1. In other words, I just have a positive 3 halves. So the rate of change is 3 over 2. In other words, the slope between these 2 points would be 3 over 2. Now let's calculate the average rate of change over the interval from 0 to 2. So when the x values, again I have the change in y over the change in x. So how are the x changing? They're changing from 0 to 2, so 0 minus 2. And when x is 0, y was 3. And when x is 2, y is 12, up here. So this tells me I have negative 9 over negative 2, or I have a positive 4 1/2. So what is this telling us? Well, it's telling us since these two numbers are not the same, that the rate of change is not constant, okay? Like in a linear function, I said we had a constant rate of change. Well, in an exponential function, we do not have a constant rate of change. In fact, we saw those graphs, they either start to grow very slowly and then speed way up, or they decrease, decay very quickly and then start to decay very slow. And you end up with curves that look like that. They're not straight lines, therefore they don't have a consistent rate of change. So the form of an exponential function, and this should look very familiar, okay? Here's your output, here's your input, your y and your x. The initial value is a, and the growth or decay factor is b, depending on if b is greater than 1 or if it's between 0 and 1. Remember, a decay factor is always between 0 and 1, and a growth factor is always greater than 1. So let's take a look. Can we determine the y-intercept of the following functions and tell whether it's increasing or decreasing, growth or decay, and then sketch the graph real quick. So this is really, really easy. Remember, the y-intercept is always the starting point or the initial value. Well, the initial value is always this a piece. So in this example here, f of x equals 17 times 4 to the x, the starting value is that 17. So that means that is the y-intercept. And is this increasing or decreasing? Well, to determine if it's increasing or decreasing, I look at the piece that has the exponent with it. And I determine if that piece is greater than 1 or between 0 and 1. In this case, it's greater than 1. Therefore, this is increasing. Which means it hits the y-axis somewhere around 17. And since it's increasing, it starts over here and zips right up through 17. So the y-intercept in number 2, p of t equals 120 times 4 over 7 to the t. The y-intercept, again, is that starting point, 120. Is it increasing or decreasing? Well, I look here. 4 over 7, it's 4/7. That's not quite 1. It's between 0 and 1. Therefore, this is decreasing. So at 120 on my y-axis, this graph is going to decrease, which means it gets small very fast and then comes very close to that x-axis, but never touches it. So again, on this last one, y equals 36 times 3 over 2 to the x. The y-intercept is 36. And don't be fooled by the fraction. 3 over 2 is greater than 1, which means that this function is increasing. And let's call this 36 right here. And that means our graph would go like this and start shooting up like that. And it's increasing. So can we determine an exponential function based on just other information, like a table or something? And the answer is clearly yes. When we find an exponential function, we always just want it to be in the form f of x equals ab to the x, or y equals ab to the x, in that form. Remember, where a is the initial value and b is the growth or decay factor. Okay, it's growth when b is greater than 1, and that's growth. And it's decay when it's between 0 and 1. Okay, so how do I dissect this table here and try to determine what my function is going to be? Let me just start with f of x. The initial value is when x is 0. Right? That's where the y-intercept is. When x is 0, the y-intercept here is 5. So the initial starting value of this function is 5. So that's the a, right? Let's do this. Y equals ab to the x. That a is that 5. So the question is now, how am I growing? Or am I not? Is this growing or decaying? And it looks like it's growing. So from 5 I go to 10. Well, I could add 5 or I could multiply by 2. From 10 to 20, well, I can't add 5 that time, but I could multiply it by 2 again. From 20 to 40, that looks like multiply by 2. From 40 to 80, that's multiply by 2. So it looks like the growth factor here is going to be 2. That's how it's growing. It's doubling, right? So times 2 every time. And lastly, I put the variable x there. So I could determine right now where this would be when x is 16, when it's 5, when it's 200. It doesn't matter. Okay, I could figure out what this would be. So it's quite easy to create the function based on information. Just you need to know the initial value and the growth or decay factor, and really that's it. All right, so we're going to play a lot more with these functions tomorrow in class. Until then, I will see you.